So here is a quick example of a simulation you can run in a finite element analysis. A car is running into a wall, as we can see here in the picture. A very complex situation where lots of things going on, the loading and on individual components, and it's very complex. And yet, with an appropriately sized finite element model, you can simulate with a high degree of accuracy on what is going on in this event or situation like this. So let's start off today's topic by taking a little quiz on what is exactly is a finite element analysis. So what is the FEA? Is it a graphic tool to make a pretty pictures? Or is it a perfect example of a garbage in or garbage out? Or is it a powerful stress analysis tool? Or is it a mathematical tool for solving boundary value problems? Or all above? So in short, we can define the finite element analysis is the situation of any given physical phenomenon using the numerical technique called finite element method or FEM. And engineers use it to reduce the number of physical prototype and experiments and to optimize components in their design phase to develop a better product faster. So let's talk about what is FEA. Then what is the big picture of what goes on. So we'll start out with a complicated problems. For example, here we have a Cal poly rose float frame, and take this problem and break it into a bunch of small pieces, as you can see here in the picture. So we can manage things in smaller pieces. We can figure out what's going on in a smaller piece, and we're going to call each of those pieces an element. So we are going to limit ourselves to a non-infinite problem. So it's a finite number of elements. There might be hundreds, there might be thousands, there might be millions of small pieces, but it's a finite number. Then we are going to look at each piece and come up with a very simple description of what's going on in that piece. And oftentimes, a linear relationship between the stress and strain or between the force and displacement, then we're going to take all of those pieces and show that they have to relate to each other using a compatibility or continuity equation. So we are going to link them together, and this will give us a large system of equation. Then we're going to assemble them into a matrix form and get an equation like what is shown here. Then we are going to solve that matrix equation. And so we can say that the basic idea of a finite element analysis is we have an equation where all the forces equals of the stiffness times all the displacement. And typically you know the stiffness of the materials because it is your structure and most of the forces, but you don't know the displacement. So in order for us to solve the problems, you have to find the inverse of the stiffness matrix K. And that will give us all the displacement. So that is the big picture in finite element analysis. So what kind of a problem that FEA can solve? Well, finite element analysis can solve any kind of a boundary value or BVP, boundary value problems, or a BVP. boundary value problem is a mathematical problem in which the quantity of interest is defined by a differential equation that covers it throughout a region. And the quantity of interest is only actually known in specific areas called the region boundary. And we need to use either the differential equation to determine the value of a quantity of interest internally, or some other method. So some common BVP or boundary value problem is in engineering include stress analysis, where we can looking for displacement and stresses internally, but we know displacement and loads externally. Then we have heat transfer, where we know a temperature and heat flux on the surface, but we don't know what's going on internally. Then we have a fluid mechanic. We have a fluid flow or fluid mechanic, or electrical and magnetic potential. All of this can also be considered to be a static or steady state problem, or a time dependent or dynamic sort of problem. So all of this can be analyzed under a steady state or static or time dependent or dynamic condition loading. So let's move on into the finite element process from the user perspective. What will you as a user will experience when you are running a finite element analysis? So in the first thing that you have to do as a user is to figure out what you don't know, and what do you know, what do you know and what you don't know, and this is how you solve any problem. So it's not different from FEA analysis. Then we define the problem first, then create a clean model. So we need to specify the geometry and the material properties with a simplified geometry, as unsimplified geometry will cause problems in finite element analysis. Then we need to define how the model restrain, from motion, or restrain from a heat transfer condition, or whatever the type of analysis that we are doing. Then we need to apply the loads to it. In the case of a mechanical system, in the case of a heat transfer analysis, it might be heat fluxes. Then we need to break up the model. We need to break up the model into pieces. As I said, with a big picture, you want to look at a finite element of a finite number of elements inside. So here is an example of a finite element mesh on the simple model we started with. You can see here. Then what we have to do is to define how you're going to analyze it. What is the relevant physics behind the problem? Then submit the job to the computer to go solve it using a software. And then finally, you will get the results in terms of the deformed shape, the stresses, the energy content in strain, and all kinds of information comes back, and then you need to determine if it is reasonable. You need to go through a post-processing operation. So that's an overview of the user perspective of finite element process. Okay, so now let's talk about what happened when a user submit a job, and what does a black box doing. Okay, so here when we talk about a black box, we refer to a FEA software. And so first, what will happen is that the computer will identify the element stiffness, element relationship inside every single element that we have defined. And the simple relationship is we got some forces acting at the point on the element. they are related to the displacements of the same point by stiffness of the element. So F equals to KD is the basic equation. F equals to K, and we have one of those for every element. So let's say that we have a 1 million element, and then we have a 1 million matrix equation initially. And then we apply some condition. We call them a continuity equation that specify that the material doesn't overlap on itself. And these are physical conditions provided that we don't have a structural failure, and we apply them. It will allows us to link all the equations that are all in the element. So when we link them together, we end up with a single matrix equation, F equals to KD, and we notice that it all caps now. And then we apply some boundary condition. So we specify what points are actually non-displacement, and we do that for a computational reason. We actually modify the stiffness matrix and the displacement vector and the force vector. And what we do next, we finally take the inverse of a KBC matrix, and that allows us to come up with a vector of known as a displacement, DBC, and then we do the post processing. So we go back to each element, we interpolate or insert. Or insert local displacement and stresses in them. Okay, so let's go over here some basic FEA terminology. We have here a finite element analysis model, as we can see in the figure here, and we can identify an element. We can identify an element as being a single piece, like what we can see in the yellow region here. Okay, we can identify an element as being a single piece of the structure shown here, and another key term is a node. You can see a node here that can be defined as a point where elements attach or meet each other or on the boundary of an element. And another important term is a boundary condition. A boundary condition or constraint. This is where we specify a non-value of a displacement, and then we have got another loading or another loads, and these are forces or other types of loads that applied to a node. And here we have examples of a 3D model of a complex two-story building. Okay, one of the first things to appreciate about loading in finite element analysis that all the loading is applied to the nodes in the model mesh. So when using a modern graphical user interface in the pre-processor, this might not be obvious. As we can see in most cases, we will be applying a load geometric entities such as surfaces and solid faces. And functionality in the preprocessor allows nodes present in the mesh to be associated with the geometric surface or a face. And if we mesh to achieve a finer mesh, for example, the old one are deleted, but the new nodes are associated with the surface or face, and hence to any loading that is applied. And here we have some other terms that are going to be important to know. We start out with a degree of freedom. How can we define a degree of freedom, or DOF? A degree of freedom is, in the case of stress analysis, is simply the displacement of a node that, and it is the displacement that is specifically resisted by the element that the node is attached to. But more generally, you can think of a degree of freedom, or DOF, as some property of a node, like the temperature, or electrical charge, that we can relate to the attached element stiffness matrix. And the next important term would be a nodal displacement vector. This is also known as the degree of freedom, and it's what I had mentioned before, a little d or a big D in earlier slides. It is the vector of all the degrees of freedom, the vector of all degrees of freedom at the node in the element or the model, at all the node or an element of the model. So that that would be the displacement in the x, y, and z direction for a 3D model, or perhaps a rotation about a certain axis, rotation about certain axis, or perhaps its temperature for a thermal analysis. And then we have another load vector, and this corresponds to the displacement vector, and it's the vector of all of the components of the load at all of the nodes. And so if we look at the displacement vector, we have a translation in x, y, and z at nodes 1, 2, and 3, and then we would have a load vector that correspond to that, to which would be the force in the direction x, y, z, and just corresponding to nodes 1, 2, and 3. And then we have a stiffness matrix that can be defined as what relates the displacement vector to the nodal force vector. So the stiffness matrix is always a square matrix, and it has the number of column and rows that correspond to the total number of degrees of freedom in the element or in the entire model. So the lowercase, by the way, throughout here, I'm using to indicate the element properties, and the uppercase will correspond to the whole system properties after we assemble them. And then finally, we have a singular matrix. It is another important concept that we need to have in FEA. And this is a matrix that simply cannot be inverted. A matrix that cannot be inverted. And we can evaluate it by determining the determinant of the matrix. And if the determinant is 0, then the matrix cannot be inverted. But it means something even more important in FEA. It means that there is no unique solution to the system. There is no unique solution to the system of equation that the matrix represents, in that the matrix represents, that is typically caused by a problem in which you haven't fully tied things down. So if we apply a force to a system, and we expect it to be static, but they are improper constraint on the system, then the system will move, or in finite element analysis terms, we can say that we will have a singular matrix, and then as a result, we cannot solve the problem.